Hi everybody, I'm William Rowe of Nutrisource Diagnostics. It's great to be here in Salt Lake City. We came down here from Canada because we wanted a taste of the tropics. It's about minus 30 back home, so really like the temperate climate around here. One housekeeping announcement that Adam asked me to pass along. The Accra photo booth has not had any pictures taken yet, and as a result, GOED cannot hand out the iPad or the iTunes gift cards they would like to hand out as part of that promotion. So please be sure to visit that. It's located around the corner down the hallway here, apparently, and you can ask any of the GOED team for further direction and instruction on that. In terms of the session here, as a follow-up to Ellen's call to action in terms of messaging around omega-3s to the consumer, to the marketplace, it's a perfect segue into our final segment of the day, and it hasn't been lost upon me or the group of speakers that we are standing in the way of free drinks and happy hour. So we're going to keep pace as best we can as we move along. But ultimately, we're here to hear about the state of the science. And our first speaker in that regard is Dr. Skattebol. And he holds his MD degree as well as a PhD in pharmacology, both of which are from State University of New York at Buffalo. He has over 17 years of experience working in the pharmaceutical industry at many different levels, and he joined Trig Pharma as Chief Medical Officer in June 2010.
Well, thank you for that introduction. And, oops, that's not. Well, my introduction title slide's not showing, but doesn't matter. What I'm going to speak to you about today is, is inflammation. And uncontrolled inflammation plays a much unappreciated role in a number of diseases that traditionally haven't been regarded as inflammatory diseases, such as atherosclerosis, cancer, asthma, various neurodegenerative disorders such as Alzheimer's or Parkinson's. And what I will be trying to explain in the 15 minutes that I've been allotted is how inflammation really comes to be and what role omega-3 fatty acids play in it. Now, to use 15 minutes on such an enormous topic is really doing it a grave disjustice. But to give it a little history, inflammation was first described as far back as the 1st century by Celsus, and he described what he regarded as the 4 cardinal signs of inflammation as being heat, redness, swelling, and pain. And it wasn't until a few hundred years later that loss of function was added. And for many, many years, it was thought that inflammation was something that happened acutely and then it went over by itself. It was a passive resolution process. Now that turns out not to be the case. And what we see is that there are specific mediators that actually mediate the resolution of acute inflammation over to the state of resolution or back to homeostasis. Now occasionally this doesn't happen and we wind up in a state of chronic inflammation. Chronic inflammation ultimately leads to fibrosis or scarring, loss of function, which leads to a number of those diseases that I mentioned a few seconds ago. Now, if we want to look into the biochemistry of inflammation, we have to go down to the cellular level. And all cells in the body are made up or have a cell membrane that is made up of a lipid bilayer. And the lipid bilayer basically protects the internal environment from the external one and vice versa. The bilayer is made up of phospholipids that align themselves with their hydrophilic head towards the aqueous external environment as well as the aqueous internal environment. And then the hydrophobic tails of the phospholipids, which are made up primarily of fatty acids, make this sandwich type of internal area here. Now, what happens when we have an inflammatory response is that we trigger phospholipase A2, which then cleaves fatty acids off of the lipid bilayer. Now, in most cases, this fatty acid will be arachidonic acid because it's the most abundant fatty acid in the lipid bilayer. And the arachidonic acid is then attacked or worked on by various either cyclooxygenases or lipoxygenases to give rise to potent eicosanoids, be it prostaglandins, thromboxanes, or leukotrienes. Now, in the event that the subject at hand who has lent us his cell membrane here has listened to dietary advice and has eaten a diet high in omega-3 fatty acids, this person will have a fair amount of EPA or DHA in the cell membrane. And phospholipase A2, being a non-discriminatory enzyme, will equally easily cleave off EPA and DHA. And the same enzymes that work on arachidonic acid will do their magic on EPA and DHA, but they will give rise to much less potent eicosanoids. So the premise of the so-called anti-inflammatory or the inflammatory lowering effects of omega-3 fatty acids is simply the fact that when they're cleaved from the cell membrane, they give rise to eicosanoids that are less potent. Now, as inflammation goes on, there's an interesting thing that happens at a cellular level, and that is that there's a shift from enzymes producing these eicosanoids to enzymes working on arachidonic acid, giving something called, or compounds called lipoxins. In the event that it's EPA that is worked on, they give rise to compounds called resolvins, and they're called E-resolvins to depict that they come from EPA. Similarly, DHA gives also rise to resolvins, but in addition, protectins and maresins. And if our subject is also on a regimen of low-dose aspirin, known to acetylate the COX-2 enzyme, we can get so-called aspirin-triggered resolvins and protectins. Now, common to all of these compounds is that they are not only anti-inflammatory, but they are pro-resolving. Now, what does that really mean? So let's take a look at the time continuum here on what happens. So we have an acute inflammatory stimulus. Very, very rapidly in the course of seconds to minutes, we wind up with edema. This is one of the cardinal signs that Celsus described 2,000 years ago. This is due to the leakage from, if it's trauma, leakage from cells, if it's a microbial invasion, it's endotoxins. These produce edema. They also have another effect, is that they send a signal to a type of white blood cells called neutrophils to come and invade the area of inflammation. They arrive at the scene and they immediately start producing more of these pro-inflammatory compounds that we talked about to begin with, further sort of worsening the inflammatory response. Now, what then happens is, as time goes by, these neutrophils interact with platelets, and this causes a shift called a lipid mediator class switch. So they then switch from producing these pro-inflammatory eicosanoids to resolving and hence anti-inflammatory compounds. Now, what these compounds also do is that they send a signal to neutrophils that are on their way to the site of inflammation, say, no, don't come, you're not needed anymore. And signals to another type of white blood cell called monocytes that they are needed at the site. So the monocytes arrive into the area of inflammation. They then quickly differentiate into macrophages. Macrophages are phagocytic. That means that they engulf foreign material, cells that are dead, etc. And the macrophages essentially mop up this war zone and are ultimately carried away with the lymph, and we are back to where we want it to be, namely at a homeostatic state. So what I just described now is sort of the traditional picture, although the resolvins have only been described since about the year 2000, 2001. But lately there are things that have arrived, and they're sort of building on previous knowledge. Namely, we're again looking here at the lipid bilayer. And there are areas in the bilayer that are more densely packed. And these have been described as lipid rafts. Now, lipid rafts are involved in cellular immunity. They're also involved in the transmission of inflammatory signals. What EPA and DHA does is that because of their bulkiness, it causes the lipid bilayer to become more fluid. And hence it disrupts the rafts, and these rafts also need to interact. So these rafts are floating around in the lipid bilayer, and as the lipid bilayer is more and more fluid, there's less chance of them interacting with each other. Also in the lipid bilayer, there are embedded a number of receptors. And one of the receptors, or the receptor types, is the toll-like receptor here. Now, toll-like receptors are essentially receptors for inflammatory stimuli. They are agonized by various external substances that are pro-inflammatory. They stimulate the receptor, and the receptor increases the production of a protein called nuclear factor kappa B. And nuclear factor kappa B seems to be the common denominator that sort of where a number of different inflammatory signals feed into. And what nuclear factor kappa B then does is that goes into the nucleus of the cell, interacts with DNA, and gets the DNA there to increase translation of different pro-inflammatory mediators, as well as upregulating enzymes that produce these inflammatory mediators. So clearly, if we were able to inhibit nuclear factor kappa B, that would be a good thing. And when we have more EPA and DHA in the cell membrane, we're ultimately going to get more of it in the cytosol due to our friend phospholipase A2. And free EPA and DHA interacts with a receptor called PPAR gamma, and PPAR gamma will interact with nuclear factor kappa B, decreasing it. We also have, possibly most exciting, is another receptor called GPR120. It stands for G protein coupled receptor 120, and it is actually an omega-3 fatty acid receptor. It's found mainly in adipocytes, which are fat cells, and what it does there is that it increases the uptake of glucose from the blood. This is important. However, unfortunately, adipocytes only amount to about 5 to 10% of the glucose metabolism, the rest of it being taken up by muscle cells, and GPR120 is not found there. But more importantly is that on macrophages, as you can see here, when GPR120 is stimulated, it ultimately leads to the inhibition of nuclear factor kappa B. And nuclear factor kappa B, as I mentioned earlier, produces inflammatory compounds called cytokines. And these cytokines lead to increased insulin resistance. This is not a good thing. In this experiment here from Jerry Alefsky's lab in California, they looked at the importance of GPR120 in a lab animal model, where normally these lab animals will, when they're fed a high-fat diet, will become quite obese. By stimulating GPR120, They were able to show the anti-inflammatory effect as well as the insulin sensitizing effect in these animals, leading to animals that did not put on weight and that were insulin sensitive. In animals that lacked GPR 120, these animals put on weight and became very insulin resistant. Now, in a clinical correlate to this, it's actually been shown that approximately 3% of the obese population lacks a functional GPR 120 receptor. So, in summary, and I'm not going to read through this slide that I've borrowed from an excellent review by Phil Calder. So if anybody wants to read essentially what I've covered here and a little more, I highly recommend this, this review article that came out last year. But to sort of summarize and try to visualize, imagine you have cell membranes that have a higher than normal concentrator or a higher than regular concentration of EPA and DHA. When an inflammatory stimulus comes around, there's a higher chance that an EPA or a DHA molecule is cleaved off instead of arachidonic acid. You'll then get a weaker inflammatory response. But it's important to remember that you will get an inflammatory response because EPA and DHA do give rise to eicosanoids. But you will have more EPA and DHA to also produce resolvins and protectins. You'll also have a more fluid membrane, which hinders the lipid rafts from interacting. You'll also have more EPA and DHA that can interact with PPAR receptors, which inhibit nuclear factor kappa B. And you'll have more EPA and DHA that can interact with GPR 120, which again inhibits nuclear factor kappa B. And all of these things result in less inflammation. And with that, I will turn the podium over to the next speaker. Thank you.